Hello dear mathematicians, in this discussion we are going to be looking at the solution of the Laplace equation, and we shall be using the method of separation of variables. The guiding question says a square plate is bounded by the lines x is equal to 0, y is equal to 0, x is equal to 1 and y is equal to 1. We are told to apply the Laplace equation uxx plus uyy is equal to 0, or del 2u del x2 plus del 2u by del y2 is equal to 0 to determine the potential distribution uxy over the plate, which has been subject to the following boundary conditions. U is equal to 0 when x is equal to 0 for values of y between 0 and 1 inclusive. Then when x is equal to 1, u is equal to 0, also for the values of y between 0 and 1 inclusive. Then finally, we also have u is equal to 0 when y is equal to 0, and u is equal to 4 when y is equal to 1, for values of 0, for values of x between 0 and 1 inclusive. So we can right away go to the solution to this problem. So let's write our partial differential equation. Del x del 2 u del y squared is equal to 0. We are going to call this equation 1. And then we are going to assume a solution to this PDE. So let the solution be, uxy equal to x of x, then y of y. So whereby x is the function of x only and y is the function of y only. So to simplify this is going to be then u is going to equal to xy. This is a simplified case. So we are going to call this equation 2. So now we are going to partially differentiate. Okay, let's take partial differentiation of partially differentiate the function in 2. So equation 2. So meaning del 2u del x squared, which is equal to del, okay, del x of del u del what? Del x. Okay, this is going to be I'm going to partially differentiate u with respect to x, okay, 2 times. So what is this going to become is x double prime y. We are keeping y a constant and differentiating u with respect to x. Let's do the same with y. So we'll have del 2u del y squared, which will be del y. Okay, let's write this properly. Del y, okay, by del u, okay, del y, and this is giving us, we are partially differentiating u with respect to y, keeping x a constant. So I will have x y double prime. Let me call this equation 3. So now I'm going to put equation 3, okay, in 1. So if I put 3 in 1, what does that mean? Wherever I have x double prime y, I put it on the second partial derivative of u with respect to x, and where I have the second partial derivative of y, I mean of u with respect to y, I substitute there x y double prime. So this is going to be x double prime y plus x y double prime is equal to 0. So I do separate variables. So separation of variables will give me x double prime y is equal to negative xy double prime. So furthermore, I'll have x double prime by x is equal to negative y double prime by y. So now what I'm going to do is to let x double prime by x equal to negative y double prime by y equal to what? To equal to, we are going to equate it to a constant. A constant, say, lambda. Okay, but a little more consideration will show that case 1, okay, and case 2, which involve lambda greater than 0 and lambda is equal to 0, will, okay, this consideration will show that case 1 and 2, lambda greater than 0, lambda is equal to 0, will not yield a desirable solution. In other words, here we'll find that the solutions that we shall get shall be in the form of u equivalent to 0, which represent the distribution at the ends, okay? The distribution at the ends of the bar and at points where x is equal to 0 and y is equal to 0. And that shall not give us what we want. We want a solution that is going to represent x and y both varying, and this is usually giving us an oscillating or oscillatory solution. So there will be no oscillatory solution. So we'll find that it is only lambda less than 0, okay, which will give an oscillatory solution. So this means we can say let lambda equal to negative p squared. So this is still a constant, okay? We haven't changed anything. So if double prime or on x by x is equal to negative y double prime of y is equal to negative p squared, then you can formulate two ordinary differential equations. I'll have x double prime plus p squared, x is equal to 0, and I'll have y double prime minus p squared, y is equal to 0. So solving the ordinary differential equation, differential equations, we will first of all use auxiliary equations, whereby for this case we'll have m squared plus p squared is equal to 0, and this will give us what? M is equal to plus or minus jp, okay? J is a complex number, so we will find ourselves with x equivalent to a cos px plus b sin px. Then what about this side, whereby m squared minus p squared for the case of y, this is equal to 0, and m is going to be plus or minus p, and then the solution becomes alpha exponential py plus beta exponential negative py. So alpha and beta are just arbitrary constants, a and b are just constants. So if I consider all this to be equation, this was equation 3, so I will call this equation 4. So that means combining the above equations, will generate a solution, a general solution, which is u xy is equal to a cos px plus b sin px multiplied by alpha exponential py plus beta exponential negative py. So that is the term that we have now. So a little more manipulation of y will give. So it gives y is equal to, first of all, we have alpha exponential py plus beta exponential negative py will be equated to, when we introduce the hyperbolic functions, so we'll have c cos py plus d hyperbolic sine py. So if I do a lot of manipulation in this, I'll find myself generating this equation. So you can try it, because you know that cos, for example, py, okay, let me say, yes, this is going to be exponential py plus exponential negative py, everything out of 2, and then hyperbolic sine py is equal to exponential py minus exponential negative py, everything out of 2. So combine this and then have other constants, then you'll find yourself getting cos py plus, okay, c cos py plus d sine py. And so, so more manipulation by introducing a phase shifted hyperbolic sine function will give y is equal to, you will see, c cos py plus d sine py will equal to, with a phase shifted hyperbolic sine function, I will have a constant times hyperbolic sine py plus phi. Okay, so that means the solution becomes u xy equal to a cos px plus b sin px, okay, times e, which is a constant, an arbitrary constant, times the hyperbolic sine p y plus the phase. So now I'm going to combine the three constants by saying let capital P equal to E and Q equal to BE, meaning that the general solution will still equal to, I'll have a P cos Px plus Q sin Px, then I'll have a hyperbolic function of sine P, okay, into y plus phi. Now I start apply the boundary conditions. So let's apply the boundary conditions. One, the first boundary condition, we are told that u is equal to 0 when x is equal to 0. And this is for values of 0 less y less what? Less 1. So when we apply a 0 here, we'll have sine 0 giving us a 0. We'll have a p cos 0 giving us p. So I will find that ourselves are going to be having 0 is equal to p, okay, times the hyperbolic sine p into y plus phi. So for this to hold, okay, for all values of y in the range 0 less or equal to y less or equal to 1, okay, then p Okay, let us say that we have the first case, the hyperbolic sine p y plus 5, okay, cannot equal to 0. Yes, okay. So it leaves us with a choice that p can be the only component that shall be equal to p will equal to 0. So if p becomes 0, then the solution becomes uxy will equal to 2 sine px, okay, then times the hyperbolic sine function. Then the second boundary condition, we are told that when x is equal to 1, u is equal to 0. And this is still true for the range of values between 0 and 1. Okay, so when we substitute in here the values, x is equal to 1, I'll have two sine, okay, this is going to be 2 sine p, then we take a hyperbolic sine function of p into 1 phi is equal. Again, for this to hold, okay, for all values of 0 less or equal to y less or equal to 1, then we'll find that sine, okay, or the hyperbolic sine y plus phi cannot equal to 0, 2 cannot equal to 0, because if that happens, then we shall have no solution. So it leaves us with the only choice of saying that sine p is equal to what? Is equal to 0, which is only possible if p is equal to p is equal to any what? Any pi, whereby n is equal to 1, 2, 3, and so on. We can say p, this small p is equal to any pi, and we call it a what? We call it an equation star somewhere there that we are going to recall later on when we are writing our final expression. And then let's go to the third boundary condition. The third boundary condition says that u is equal to 0 when y is equal to 0. So this is true for the range of values of x, 0 less x less what? Less 1. So let's substitute the values of what? Of y is equal to 0 in our general expression. The general expression that we have so far is this. So we'll have u 0 of 0. This is u0. It is actually ux. So ux0 will equal to 2 sine px. Then we are multiplying it by sine, the hyperbolic sine of p, 0 plus phi. And we are saying that this is equal to 0. So we'll have 2 sine px, hyperbolic sine p, then we shall have phi, and this is equal to 0. We said that again, we said that 2 itself cannot equal to 0. 2 cannot equal to 0, because if that happens, we shall have no solution. Sine px cannot equal to 0. That is true for values of 0 less x less what? Less 1. If this is to hold, then sine p x cannot equal to 0. Gives us with the only choice of saying that the hyperbolic sine p phi is the only value that is going to be what? Going to be 0. And this is true if phi is equal to 0, because p itself will not equal to 0. So what does that tell us? The general solution becomes uxy will equal to 2 sine px. Then we shall have the hyperbolic sine of hyperbolic sine p py. Yes. So once this is true, okay. Once this is true, what we are going to do is to do what? Is to come and now write the general expression. So if we now put in n from the equation star, okay, from star, n pi is equal to p. So we shall just substitute and say that un of x, since we are going to be having very many values of u, okay, so we shall have un x of y, I mean xy is equal to the sum from n is equal to 1 up to infinity of sine, this is 2n sine n pi, okay, x, then hyperbolic sine h n pi of y. So once we are here, we shall be in a position to consider the fourth boundary condition, which says that u of x1 is equal to 4, and this is always the function of x. So this is going to be so much paramount because it is going to help us to determine the coefficient 2n. So the Fourier coefficient to n will equal to 2 times the mean value of f of x sine n pi x. Okay, remember this is going to be divided by the hyperbolic sine, okay, n pi y. So if that is the case, remember this is usually divided by a. This is usually divided by a, and this is a, but we know that a is equal to 1. This is the maximum value of x that we are taking in this case is equal to 1. Therefore, we'll have 2n. This is a hyperbolic. So hyperbolic sine n pi y, okay, out of 1 will equal to 2 divided by 1. Then integrating from 0 to 1, of course we are taking the what? The mean value of f of x sine n pi x. So meaning we shall be integrating, we will get anyway 2 divided by the period, okay? So the period for this is going to be 1. 0 plus 1, we will have 1, okay? Then 2 divided by 1, integral of f of x sine n pi x with respect to x. So we shall have 2n sine times y, but y for this case is going to equal to 1. Since we are talking about 2n being a constant, we are going to substitute this y with 1 because also the maximum value of y is going to be what? Is going to be 1. So this is equal to 2, okay? Integrating from 0 to 1 of 4, then sine n pi x with respect to x. So that means I'm going to have 2n equivalent to out of the hyperbolic sine n pi. So if I integrate this, I'm going to have negative cosine, negative cos n pi x out of n pi from 0 to 1. So if I substitute these limits, I'm going to have 8 out of what? Out of pi times sine. This is n pi n, what has come outside, inside these brackets, sine, hyperbolic sine n pi. Then I'll have negative cos n pi plus 1, because cos of 0 is equal to 1. This is 2n. So 2n, therefore, will be, I'm going to take n, and I'm going to get negative 1 to power n. So this is going to be 8 divided by n pi, hyperbolic sine n pi, into 1 minus negative 1 power n. Okay? So remember that when n is even, then 2n will become 0, because this is going to be 1, then 1 minus 1, it becomes 0, times this, it becomes 0. And then n, when n is equal to an odd number, then 2n will be 2 times 8 divided by n pi, hyperbolic sine n what? N pi. So finally, 2n over 16 out of n pi, hyperbolic sine n pi, is going to be taken because we know this is a Fourier coefficient that is on a sine. So when you have a sine, remember it's an odd function. And if you're looking for the coefficient and it is on an odd function, then that means you are going to you're going to find yourself, if you're dealing, for example, this train is on a sine and you have gotten a value of 2n for which n is odd, then you'll be right. But if it was, if we are dealing with an even function, then it would go to 0. For example, if this 2n was on a cos, then we would take this. Since we'll be dealing with a cosine, which is an even function. But here we are dealing with an odd function, and therefore I will find that u of xy will therefore equal to summation from n is equal to 1 for n equal to odd numbers up to infinity. I will have a 16 out of pi. Then we'll have, this becomes now a hyperbolic cosec. So this becomes cosec, okay, hyperbolic cosec n pi, everything out of n. Then we are multiplying it by sine n pi x. Then remember we had our function here that is hyperbolic sine n pi y. So we replace it here so that we have the final solution. So hyperbolic sine n pi y. So finally, the final solution becomes u xy equivalent to 16 out of pi. The summation for n being odd, okay, for n as odd numbers ranging from 1 up to infinity. So n pi, okay, divided by n, we have sine n pi x and hyperbolic sine n pi. So this is our final solution.